starting with the S block elements, that is alkali metals. So in the alkali metals, that is the first we'll come to the members of the group. Except hydrogen, the other six elements of the group, that is group 1, that is your lithium, sodium, potassium, rubidium, cesium and francium are called all alkali metals. Alright, since their oxides and hydroxides are soluble in water and form strong alkalis. But francium is, however, radioactive in nature. Alright, so the general electronic configuration of alkali metals is NS1, that is noble gas, any noble gas. Then after that NS1, where the value of N will range from 2 to 7, that is second period to seventh period, we can say that, because the first period I said, that is hydrogen is there. So except hydrogen, due to the presence of one or more unpaired electrons, all alkali metals are paramagnetic, but their salts are diamagnetic in nature, we can say that. Their salts are diamagnetic. The remaining elements are much less abundant. What you can say is that if you see, rubidium is the 23rd and cesium is the 46th and beryllium is the 51st most abundant element by weight in the Earth's crust. Got it? Alkali and alkaline earth metals occur abundantly in nature otherwise. Alright, they occur abundantly in nature. For example, calcium is the 5th, magnesium is the 6th, and sodium is the 7th, potassium is the 8th, barium is 14th, and strontium is 15th most abundant element by weight in the Earth's crust. Alright, sodium and magnesium are also present in relatively large amount in seawater. Brine wells, brine means NaCl, that salt, we can say that, and a few salt lakes, we can say that. Clear? So in this way, what you find is that the element francium was discovered quite later in 1939 by Perry at the Curie Institute, Paris. We can say that. Got it? That is, your francium was discovered. That is, actinium gives francium plus helium. Actually, in this way, it was being discovered. When radioactive decay goes of actinium, when actinium undergoes radioactive decay, it gives francium and helium. That is Fr223, we can say that, which is the longest lived isotope, we can say that. Now the first element of the group differs considerably from rest of the elements. It's very important, listen carefully. The first element of a group differs considerably from the rest of the elements, that is heavier elements of the same group. This anomalous behavior is due to small atomic and ionic radii. This anomalous behavior is due to high electronegativity and ionization enthalpy, due to high polarizing power of its cation and absence of d electrons in its valence shell. Alright, again I repeat, due to the small atomic and ionic size, the anomalous behavior is due to high electronegativity and ionization enthalpy, due to the high polarization power and of its cation and absence of d electrons in its valence shell. Thus, lithium differs from rest of the alkali metals, that is sodium, potassium, rubidium, and cesium. In this particular manner, we can say that. Clear? So, if you see, that is lithium has got diagonal relationship with magnesium. Lithium, that is, it has got similarity in electropositive character. It has got similarity in atomic or ionic radii. It has got similarity in polarizing power. Alright, that is, it has lithium has got a relationship with magnesium, that is diagonal relationship, we can say that, due to similarity in electropositive character, due to similarity in atomic or ionic radii, due to similarity in polarizing power, we can say that. Now there are several compounds of alkali metals, we can say that, several compounds of alkali metals like Salvine, we can say KCl, a mixture of KCl and NaCl, we can say, and we have got carnallite, KCl.MgCl2.6H2O, we have got feldspar, K2O.Al2O3.6 SiO2, we can say that. Clear? In this way, many more compounds are there of that is your alkali metals. Many more compounds are there, we can say that. Now, if you see, the atomic radii of alkali metals are the largest. The atomic radii are the largest after inert gases in the respective periods. Alright, both atomic and ionic radii increase down the group from lithium to cesium as the number of inner filled shells and screening effect increases. Alright, So that is any screening effect. If it is increasing and the inner filled shells is increasing, number of shells is increasing, then what you find is that the atomic radius and ionic radius also increases down the group. The enthalpy of hydration of alkali metals ions decreases with increase in its ionic radii. Alright, that is Li plus is greater than Na plus is greater than K plus is greater than Rb plus is greater than Cs plus. In other words, the degree of hydration decreases down the group. Degree of hydration, it is decreasing down the group from lithium ion to cesium ion considerably, we can say that. That is lithium ion to cesium ion. Consequently, the radii of the hydrated ion decrease in the order. Alright, the radii of the hydrated ions decrease in the order. Li plus is greater than Na plus is greater than K plus greater than Rb plus and Cs plus, we can say that. Further, since Li has maximum degree of hydration, therefore several Li salts are hydrated like LiClO4.3H2O, Li2CO3.3H2O, LiCl.2H2O, etc. We can say that. Clear? So next is the first ionization enthalpy delta H1 of alkali metals is quite low and decreases further down the group due to increase in atomic size and shielding effect, we can say that. Further, due to inert gas configuration of the unipositive ions, the second ionization enthalpy of alkali metals are very high and decrease down the group. The first ionization enthalpy, what I said, is quite low, but the second ionization enthalpy due to inert gas configuration. Listen carefully. You have read it in bonding chapter. Bonding, I am saying. You have read it in periodic properties chapter. So from there itself I am saying that is due to the inert gas configuration. When it loses one electron, it assumes the configuration of an inert gas. So due to inert gas configuration of the unipositive ions of the second ionization enthalpy of alkali metals are very high and decrease down the group from lithium to cesium. Got it? All alkali metals are strongly electropositive due to their low ionization enthalpies. Strongly electropositive. Further, the electropositive character increases down the group as the ionization enthalpy decreases. Thus, francium is the most metallic and electropositive element in the periodic table. Consequently, all the alkali metals uniformly show an oxidation state of +1. We can say that all alkali metals, we are saying Na plus C, Li plus K plus, all having that is uniformly an oxidation state of +1, we can say that. Clear? So in this way, due to the low ionization enthalpy, as I said you, the ionization enthalpies of alkali metals decreases progressively as you are moving down the group from lithium to cesium. The second ionization enthalpy of alkali metals are high, that also I have discussed with you. They form unipositive ions. The elements of this group are typical metals which are soft, malleable and ductile solids. They can be easily cut with a knife. Alright, and if you see the melting and boiling points, the melting and boiling points of alkali metals are quite low and decreases further down the group due to weakening of the metallic bonds. Because the atomic size increases, the metallic bonds becomes weaker. Thus, amongst alkali metals, lithium has the highest and the cesium has the lowest melting point and boiling point, while francium is liquid at room temperature, we can say that. The densities of alkali metals are quite low. Lithium, sodium and potassium are even lighter than water. The densities, however, increase down the group from lithium to cesium due to an increase in their atomic mass, which more than compensates the bigger atomic size. Potassium, however, is lighter than sodium, probably due to abnormal increase in atomic size of potassium as compared to its atomic mass. As we come down the group, what happens is that the density, however, increases. Alright, that is the reason is that lithium to cesium, due to increase in atomic mass, not only the atomic size is increasing, but the atomic mass is also increasing. So, due to an increase in the atomic mass, which compensates the bigger atomic size. What I said you, not only the atomic size is increasing, but also the atomic mass is increasing. Got it? So, the atomic mass compensates the bigger atomic size. However, that is potassium, however, is lighter than sodium due to an abnormal increase in atomic size of potassium as compared to its atomic mass. Abnormal increase, why? Because sodium belongs to third period, potassium belongs to fourth period. Up to third period, the maximum capacity, it is, what is that? It is nothing but 8. The number of elements is 8. From the fourth period, it comes to be as 18. What do we have? The magic number 2, 8, 8, 18, 18, 32. So fourth period it is 18, the maximum number of elements it can be. So maximum number of electrons can be 18, we can say that accordingly. So in this way it is increasing abnormally. Due to low ionization enthalpies, all the alkali metals and the salts impart characteristic color to the flame. Yes, they impart a characteristic color, like lithium will give you crimson color, sodium yellow color, potassium pale violet color, rubidium red violet color, cesium blue color. Alright, so why it happens? On heating an alkali metal or its salt, especially chloride, due to its more volatile nature in a flame, the electrons are excited easily to higher energy levels because of absorption of energy. Electrons are excited easily to higher energy levels because of absorption of energy. When these excited electrons return to their ground state, they emit extra energy in the form of electromagnetic radiations which fall in the visible region, thereby imparting a characteristic color to the flame. First it gets excited, then after that when they come to the to the ground state, they emit some energy. The extra amount of energy is emitted. This energy corresponds to a particular spectrum in the given region. So particular color in the given spectrum. So that color we are seeing it on the flame. So hence it imparts a characteristic color to the flame. The color actually arises from electronic transitions in a short-lived species which are formed momentarily in the flame. We can say that. Again I repeat, the color actually arises from electronic transitions in a short-lived species which are generally formed momentarily in the flame. The flame is rich, a source of electrons, and in case of sodium, that is we are getting the golden yellow color, we can say that. Clear? So in this way, that is due to low ionization enthalpies, all alkali metals except Li show photoelectric effect. Photoelectric effect is a phenomena of ejection or emission of electrons from the metal surface when electromagnetic radiations are made to strike against them. So because of the strong photoelectric effect only, cesium is frequently used in solar cells. For that reason only, cesium is frequently used in solar cells, we can say that. Clear? So in this way, now due to low ionization enthalpies, alkali metals forms ionic compounds. Further, the ionic compounds ionic character increases down the group due to decreasing ionization enthalpies. Alright, due to low ionization enthalpies, alkali metals forms ionic compounds, and further the ionic character increases down the group due to decreasing ionization enthalpies. We can say that. Lithium, however, because of its high ionization energy, see, always lithium will show an abnormal behavior. Alright, due to its small size, due to the absence of d orbitals, due to low electronegativity and ionization enthalpy. So lithium will always show due to high ionization enthalpy and that is electronegativity. So lithium in that particular group, compared to other elements of that particular group, lithium will always show an anomalous behavior, a different behavior from other elements. So hence lithium, however, because of its high ionization energy forms covalent compounds. It does not form ionic compounds, it forms covalent compounds, we can say that. Got it? So due to large negative electrode potentials, alkali metals are strong reducing agents, we can say that. So the reducing power increases from sodium to cesium, but lithium is strongest reducing agent due to large enthalpy of hydration of the Li plus ion. Just now we studied that Li plus ion has got the largest hydration enthalpy. Alright, so after that hydration enthalpy decreases in that group, in the same group. I am talking about the group, I am not talking about the period, I am talking about the group now. Alright, because I am teaching you now group 1 element. So the reducing power increases from sodium to cesium, but lithium is the strongest reducing agent due to large enthalpy of hydration of Li plus ion, we can say that. So all alkali metals react with water evolving hydrogen, every alkali metals, and forming their corresponding metal hydroxides, we can say that. Clear? So that is alkali metals hydroxides are strong bases, and the solubilities and basic character increases down the group from lithium to cesium as the ionization enthalpy of the metal decreases. we can say that, as the ionization enthalpy of the metal decreases, we can say that. So so for that reason, or the electropositive character of the metal increases, thus basicity increases in the order LiOH is less than NaOH, is less than KOH, less than RbOH, and less than CSOH. So CSOH is the most basic in nature, is the most metallic in nature, we can say that. For that reason, its basic character also is the maximum, we can say that. So in this way, that is the basic character, you can see it increases in this particular order. Now, when heated with oxygen, alkali metals form different types of oxides depending upon the nature of the metal. Depending upon the nature of the metal, alkali metals get tarnished when exposed to air and moisture due to the formation of first oxides, then hydroxides, and finally carbonates. Got it? Because of these reactions, alkali metals, we can say, are stored in inert hydrocarbon solvents like petroleum, ether, and kerosene oil, which prevent them from coming in contact with air and moisture, so to say, we can say that. Clear? So next is alkali metals combine directly, all alkali metals on heating with hydrogen form ionic hydrides of the general formula MH, we can say that. All alkali metals, the reactivity of the alkali metals towards hydrogen decreases down the group from lithium to cesium due to the reason that lattice enthalpy and hence the stability of these hydrides decrease down the group. As the size of the metal cation increases, it increases, we can say that. As the size of the metal cations it increases, we can say. So for that particular purpose, all what you can say, that is alkali metals, what you find is that it forms hydrides and decreases down the group as the size metal cation increases, and the stability decreases in the order, that is LiH is greater than NaH, KH, RbH, and CSH. That is lithium hydride is most stronger hydrides compared to cesium hydride. Besides the simple hydride, lithium and sodium form complex hydrides also, like LiAlH4, you have heard it, lithium aluminum hydride. It is used as reducing agent. NaBH4, reducing agent, which are powerful reducing agents and are widely used in organic chemistry, we can say that. We will be studying in details in organic chemistry. So alkali metals combines directly with halogens to form metal halides. With the exception of lithium halides, all other alkali metal halides are ionic. Alright, all other metal halides are ionic with the exception of lithium. I told you earlier only that lithium has got an anomalous behavior. Compared to the other metals of the group, the lithium has got an anomalous behavior, so to say. So this is all about. Thank you.